Welcome to this fourth lecture on fluid mechanics for chemical engineering undergraduate students. In the previous lecture, we described the continuum hypothesis and explained when it is valid and when it can break down potentially. And we also said that in most engineering applications, it is possible to use the continuum hypothesis without any problem. And in the continuum hypothesis, we treat the velocity, the variables in the fluid such as pressure, velocity, temperature, density and so on as smooth and continuous functions of position coordinates like x, y, z as well as time. Okay. Then we started our discussion on what a fluid is. In order to do this, it is first useful to contrast the mechanical behavior of a fluid with that of a solid. So, that is what we will do. We will start again with the notion of an elastic solid, and then we will contrast the behavior of a fluid immediately after this discussion. So, what we did in the last lecture was to take a slab of a solid like a rubber, elastic solid like rubber. Imagine you have a rectangular slab, okay, and this width of this slab in this third direction. Okay, let us put a coordinate system x, y, and the third direction that is pointing out of the board is z. Okay. So, this is w and the thickness of the slab in the y direction is h, and we are going to consider a sheet or a slab such that w is very large compared to h. Okay. So, when w is very large compared to h, you need not worry about the variations in the z direction. Okay. So, all we will do is to consider a planar cross section in the xy plane. So, we will assume that we will take the xy coordinate system like this, okay, and we will assume that the slab is like here, just a cross section in the xy plane. And what we did was we imagined that this slab, this piece of elastic material is kept between two plates, okay, and the bottom plate is stationary and the top plate we want to apply a stress in the x direction, which I will denote as Fx. So, essentially what we are doing is let us consider this area of the top surface, which I am going to shade. This force in the x direction is being acted upon on the entire area, okay. Fx acts on the top surface, and let the area of the top surface be A. Okay. So, Fx is acted upon, Fx acts on the top surface, which is at y equals h, and this is at y equals 0, and this thickness is h. Okay. This is the system. One can think of doing this experiment in a lab, and I am going to discuss this as if we are doing this experiment in our mind, and then so we are doing a thought experiment, and then we are going to discuss how this solid is going to behave under the influence of applied forces. Okay. So, let us imagine this is the unstressed, suppose at some initial time the solid is unstressed, state before the force has been applied. Okay. No force has been applied in the unstressed state. Okay. And in the unstressed state, imagine that we are going to mark a line in the solid, okay, a vertical line, at a given location. Okay. And we are going to follow this the position of this line as you are going to apply a force, okay, on the top surface. So, when there is no force, there is no stress in the solid. So, this line will be a vertical line. Now, imagine that you are going to consider the same rectangular slab, okay, in between two plates, okay, and this is x and y as usual, and we are going to follow, this is in the undeformed state or the unstressed state, but now we imagine that you are applying a force. Okay. So, we start applying the force at some time t equals 0, and then we allow an interval delta t, a time interval delta t, and then watch the evolution or the motion of this line. Okay. When you apply a force to the solid on the top surface, okay, the solid responds by undergoing a deformation. So, what the solid will do is, in fact, this line, see, force is being applied only on the top surface. So, this point that was here will move here, okay, whereas this point at the bottom surface is stationary, there is no force that is applied, the solid is stuck to the bottom surface. So, this point will remain here, it will not deform. So, this line will move in general in the deformed upon application of force, this line will move like this. So, this green line is no force in the unstressed state. Okay. Whereas, this red line is when you apply a force at and then you record the motion or location of this line at a time delta t. Now, imagine applying this force for continuously on the top surface, and let us try to understand what will happen to this red line as you continuously apply the force. So, even if you were to wait for more times 2 delta t, 3 delta t, 4 delta t, a solid merely undergoes a deformation, and then once it in response to an applied force, and once it undergoes once it has underwent a deformation, it will stop deforming due to resisting elastic forces that are built in the solid. So, this, let us call this displacement of the point on the top close to the top plate as delta L. This delta L will remain the same, okay, even at higher times. Even suppose you were to measure the displacement of the top point, okay, versus a function of time. Okay. So, at time delta t, 2 delta t, 3 delta t, and so on, in a solid you will observe experimentally that the displacement of the top point remains delta L. Okay. And you can also characterize this deformation by this angle delta alpha. Okay. So, and this thickness is of course h. Okay. So, a solid responds to an applied stress by undergoing a deformation, and this deformation does the solid deformation stops after it does not continue to increase, it undergoes a finite deformation. And if you were to do experiments, okay, at different values of stresses, so this is for a given value of stress, if you were to do experiments at different values of stress or force, sorry. So, if you were to do the experiment for F1, let us call it just F, a force Fx, the displacement will be delta L. Then if you were to do 2 Fx, the displacement will be 2 delta L, and 3 Fx. If it is a purely elastic solid, you will find that the force that you apply, okay, will be directly proportional to the displacement the solid undergoes, or the displacement which is a response to the force is directly proportional to the force in a solid. Okay. So, while this is how experimentally you will characterize the deformation in a solid, in order to make the information from experiments more general, it is useful to talk in terms of a stress rather than a force. Stress is force per unit area, okay, Now, this force in this example, the force is applied in the x direction plus x direction, and the area of the surface on which force is exerted is A. Okay. So, this is simply F x divided by A. Okay. So, that is what we said in the beginning, that so the area is A. So, the area of this surface is A, okay, and this is called the stress. Okay. Now, the stress is given denoted by the symbol usually tau in fluid mechanics and in mechanics in general, continuum mechanics in general, and it is described with two subscripts. Okay. One is the subscript which is, let me write down the subscripts and explain what those two subscripts mean. Okay. The subscript x is the direction of the force. The stress is force acting on a surface per unit area. So, the force itself has a direction. This y denotes the unit normal to the surface, direction of the unit normal, unit vector if you want, to the surface on which force is acting. Force is acting. Okay. Now, in our example, the surface, we took this slab and the force was in the x direction, and the direction of the unit normal is in the plus y direction, which is traditionally denoted by the unit vector j. Okay. So, this y denotes the direction of the unit vector, which is the y, the unit vector along the y direction. So, it is the direction of the unit vector perpendicular to the surface, okay, that is called the unit normal, okay, and the x denotes the direction of the force. So, this is called stress. Okay. Stress is force per area, but we have to specify the direction of the force, okay, on the surface as well as the orientation of the surface by specifying the unit normal or the unit vector perpendicular to the surface. Okay. So, for a solid you will find that tau y x, okay, in our example tau y x is simply f x divided by A, okay, and you will find that the stress, if you do experiments, is directly proportional to the deformation, which is characterized by the angle delta alpha. Okay. Recall that you had this line, original line, unstressed case, and then deformed case. The deformation can be characterized by this angle by which this line tilts upon application of force in the x direction. Okay. This is x and this is y. So, this angle can be taken as a suitable measure of the deformation or the strain in the solid. Once a solid undergoes a deformation, we say that it is strained. Okay. So, the strain, a measure of the strain in the solid, the deformation in the solid, is the angle delta alpha. So, you will find that delta alpha, the stress that you apply is directly proportional to the inclination of this, the tilt of this line upon the application of stress, and the stress will not change in a purely elastic solid as you wait long enough. The angle will not change if you wait long enough. Even if you apply a stress continuously, the angle will still remain the same. That is because that is the nature of the solid, to resist deformation. Okay. So, it resists deformation, it undergoes some deformation, but it does not continue to deform under the application of a force. Okay. So, that is the definition of a purely elastic solid. So, let us do some simple geometry. So, this height was h. Okay. So, from this and this displacement of this line from here to here was delta L at the top plate. So, tan delta alpha from this figure is delta L by H, okay. But when you apply small enough forces, delta alpha will be small. So, when delta alpha is small, tan delta alpha is roughly proportional to delta alpha. So, this equation tells you that delta alpha is approximately delta L by H, or I can write, okay. So, that is delta L by H, that is fine. So, this stress tau y x is proportional to delta alpha. So, I can write tau y x is proportional to delta L by H, because delta alpha, this is, please do not confuse this is the proportionality sign, okay. This alpha is the angle. So, let me try to write it like this, okay. The proportionality sign slightly differently from alpha. So, tau y x is proportional to delta y L by H, okay, and you can replace the proportionality constant, proportionality sign with a constant of proportionality, that is called the modulus of elasticity, okay. This is called the modulus of elasticity, okay. So, and we can work out the dimensions or units of this quantity. Tau y x has dimensions of stress. Stress is force per unit area, force is mass times acceleration divided by area. So, stress becomes m L to the minus 1 T to the minus 2, okay. And this group is a ratio of two lengths, is dimensionless. It has no dimensions because it is length divided by length. So, strain in a solid is dimensionless, okay. So, the modulus of elasticity will have the same dimensions of stress. So, the normally dimensions of a quantity are denoted by this square bracket. So, m L to the minus 1 T to the minus 2, okay. This is the dimension, these are the dimensions of modulus of elasticity, okay, and or stress for that matter. And in SI units, okay, G is, I mean, so if you put m as kg, okay, per meter for L to the minus 1 and T to the minus 2 second square, this is called 1 Pascal, okay. So, stress and modulus of elasticity, everything is measured in Pascal, okay. So, now this, the stress is therefore directly proportional to the strain, okay. Now, previously in this simple thought experiment, we considered a slab of thickness h, but we could take a tiny thickness delta y in the y direction within the slab itself, okay. We will take a tiny thin slice. So, you take, just to illustrate, this is your slab, okay, and even within this slab you can take a tiny slice of the slab and then worry about what is the stress with respect, what is the, how does the deformation change with respect to stress within this slice, okay. So, we will do the same thing. So, we will find that tau y x is proportional to, so this within this thin slice, a line that was originally like this would have moved like this. So, let us call this delta L. So, again it will be proportional to delta L by delta y. So, in the limit, now if you take the limit when the thickness of the slice goes to 0, this becomes a derivative, okay, in calculus. So, tau y x is proportional to dl by dy, okay, and we can write this as a constant of proportionality times dl by dy. This is called the strain in the solid. So, while the previous discussion where you took a finite piece of material h is valid for that particular experiment alone, this expression is valid in general, because you can take a solid of any thickness and look at the deformation at a point or within the continuum approximation, a tiny slice of volume around a point, and then you will find that this equation is valid, okay. So, Now, let us contrast this behavior with a fluid. I am going to do the same thought experiment, have a fluid between two slabs like a viscous liquid. Let us imagine a viscous liquid like honey. Okay. Take two slabs, let us mark the coordinate systems. Again I am going to assume as before that in principle it is two slabs, okay, okay, and okay, and on the top slab you apply a force Fx. Okay. This width is very large compared to the thickness h in which the fluid is present. So, we need not worry about the variation in the z direction. So, in our scheme of things, this is x, this is y, and this is z. Okay. So, we will just consider the xy plane and we will put a colored dye in the fluid at time t equal to 0, okay, when there is no force that is exerted. Now, at time t is equal to 0 plus, you start applying a constant force Fx. Okay. So, now what we are going to do in this discussion is to look at the evolution of this colored line as a function of time when the force is being applied on the top plate, and as before the area of the top plate is A. Okay. Now, so let us imagine that after a time delta t, we look at this line. So, the bottom plate is stationary, there is no force. So, the fluid here close to the bottom plate, just adjacent to the bottom plate, will not move, while the top plate, fluid close to the top plate, since you are exerting a force, this line would have deformed like this. So, this is at a time let us say delta t, but a fluid continues to deform under the application of stresses, especially shear stresses. Okay. So, here we are applying a force on a surface, okay, and the force is parallel to the surface. Okay. So, the force is parallel, this is the surface on which the force is being applied, and these are called shear or tangential stresses, tangential forces or stresses. Force per unit area is a stress, okay, shear or tangential stresses, because it is tangential to the surface on which the force is acting. The force is tangential to the surface itself, in contrast to normal stresses which are perpendicular, as the name suggests. Okay. So, here we are applying a shear stress or shear force on a tiny slice of fluid with between two plates, and we are finding that you will find that if you do this experiment, okay, if you watch this evolution of this colored line as a function of time, this line will continue to move at later and later times. Okay. A fluid continues to deform under the application of shear stress, in contrast to a solid which deforms to some extent and then stops deforming. Okay. So, a fluid continues to deform. So, what you will find in experiment is that at 2 delta t this line will become like this, at 3 delta t this may become like this. Okay. So, if you think of this distance as delta L, okay, and this is at 2 delta t, this line is at 3 delta t, and so on. So, this line continues to deform, that means that the fluid continues to move under the application of shear stresses. We say that the fluid flows under the application of shear stress. Okay. So, you will find that if you do this experiment, that if you were to plot at t equal to 0, this line will be like here. So, I am going to draw different snapshots, t equals delta t, this line which was originally here would have moved like this, it would have moved by an angle delta alpha, and the top point would have moved by the length delta L. Okay. And at a later time t equals 3 delta t, it would have moved, okay, I am sorry, just 2 delta t, let us keep it 2 for simplicity. Okay. It would have moved 2 alpha the angle would have increased to 2 delta alpha rather, and the length of this point from its original position would be 2 delta L. Okay. So, a fluid cannot resist any shear stress. So, it continues to move upon application of shear stress. Okay. So, clearly this thought experiment suggests this can be done in a lab also, but one can do it, but here for the sake of illustration I am just doing a thought experiment. Okay. So, the stress in a fluid, unlike a solid, cannot be proportional to deformation. The reason is you can get any amount of deformation if you are prepared to wait long enough. This slice, which was originally here, underwent a deformation of delta L at time delta t, 2 delta L at time 2 delta t, and so on. So, it would keep deforming as you wait long enough. Okay. So, stress really cannot be proportional to deformation. Okay. So, what is then stress a function of? Okay. Let us slightly change the experiment. Instead of keeping, so here I am applying a force F x, same force. So, here I mean at time t equal to 0 there is no force. So, okay. Here there is no force, but at later times you are applying the same force. But now let us take this experiment. Instead of applying f x, I am applying 2 f x. You will find that even at time delta t, this line would have moved by 2 delta L. Okay. So, if you increase the force for the same amount of time that you are waiting, okay, the deformation will increase by the same amount. So, for example, if here f x was the force, here the force is 2 f x, for the same time delta t, you are finding that the deformation has doubled. Okay. So, the stress is not proportional to deformation per se, because the same amount of deformation can be obtained in a fluid at if you are prepared to wait long enough. Okay. So, even if you apply a very tiny amount of force, okay, you can get the same amount of deformation delta L if you wait sufficiently long enough. So, clearly stress is not directly proportional to deformation, indeed it is proportional to how fast the fluid deforms, or we say more clearly or more specifically the rate at which a fluid deforms. Okay. So, the stress is proportional in a fluid as this experiment suggests. So, we have that for force F x, okay, the deformation, this is the applied force, this is the deformation that one gets as we measure through the angle, was delta alpha at time delta t, 2 delta alpha at time 2 delta t, and similarly if you apply 2 f x, you get 2 delta alpha at delta t itself. Okay. So, the stress tau y x, which is the same which has the same meaning as what we had in the previous illustration for an elastic solid. This is the force in the x direction on a surface whose perpendicular is in the y direction. Okay, to the surface. So, tau y x is the stress that you are exerting on the top plate. Okay, this is simply equal to f x by a divided by a. Okay, it cannot be proportional to delta alpha, but in fact it is proportional to the rate at which alpha changes with time, delta alpha by delta t. Okay. Then this will because this is what the experimental results would suggest. If you wait for delta t for the same f of x, you get delta alpha. If you wait for 2 delta t, you get 2 delta alpha, but if you double the stress for the same delta t, okay, the deformation doubles. Okay. So, all this is captured by the simple hypothesis or proposition that the stress must be proportional to the rate of deformation. For example, in this proposition, if I double the stress, so let us say tau 1 was the stress, then delta alpha 1 was the deformation at time delta t 1. If I were to wait for 2 delta t 1 for the same stress, then say proportional to, then I would get 2 delta alpha 1 because I am keeping stress constant. If I weight 2 delta T1, since it is directly proportional, it will be 2 delta alpha 1. Okay. But if I keep 2 tau 1, okay, and I keep delta T1 the same, since it is directly proportional, the angular displacement has to increase by 2 delta alpha 1. So, all this is captured by this simple relation that tau y x must be directly proportional to delta alpha by delta t in a fluid. Okay. So, now let us look at the geometry again once again. So, this was the original line, this was the deformed line, this is delta alpha, this is delta L. But in a fluid, the top plate continues to move, because the fluid is also moving. The top plate will also, if you exert a force, the top plate will continue to move. Okay. So, this delta L, so the top plate will acquire an velocity if you apply a force to the fluid. Okay. So, it is u times delta L will be u times delta t. Okay. And this is h. Okay. So, from geometry we know that tan alpha is delta L by h, tan of delta alpha, sorry, and for small delta alpha, tan delta alpha is approximately delta alpha, small angles. This we discussed few minutes back for the case of elastic solid also. So, delta alpha is delta L by h, okay, but delta L is delta u times, so u times delta t, okay, divided by h. So, delta alpha by delta t is equal to u by h. So, u is the velocity of the plate, top plate, and h is the thickness. So, tau y x is proportional to u by h, where u is the velocity. Suppose you exert a force in the x direction on the top plate, this plate will start moving if whatever is the material that is present between the two plates is fluid, and you can characterize that motion with a velocity u of the top plate. So, this is the velocity of the top plate, and in the x direction this is the, and h is the thickness of the fluid. Okay. So, instead of taking finite thickness, we can also consider an infinitesimal thickness delta y, okay, then tau y x will be proportional to, so infinitesimal slice of fluid will be proportional to delta u by delta y, which is essentially, okay, the velocity, okay, of this top layer with respect to the bottom layer. Okay. And when all the things, when in the limit delta y tending to 0, tau y x will be proportional to, this will become a derivative, will be proportional to du dy. This is called the velocity gradient. It is the derivative of the x velocity u with respect to the y coordinate. It is called the velocity gradient. Okay. So, you can replace the proportionality symbol with a constant of proportionality, okay, and that constant of proportionality is denoted by the Greek symbol mu. It is called the viscosity of the fluid. Okay. So, a fluid, in a fluid the stress is not proportional to deformation, it is proportional to rate of deformation, and through this simple geometric analysis or argument we have shown that the rate of deformation is proportional to the velocity gradient, is equal to the velocity gradient. Therefore, tau y x, which is proportional to the velocity gradient, can be replaced by a constant mu. The proportionality sign can be replaced with a constant, which is called the viscosity of the fluid. So, what this says is that suppose we were to do this experiment with two fluids, okay, one with higher viscosity and the other with lower viscosity, okay, and you do this, you apply the same force F x on the top plate, okay, and you watch the motion of these lines at a time after a time delta t. Okay. So, if you do that, you will find that though lower viscosity fluid would have deformed more compared to the higher viscosity fluid at the same time, but if you are prepared to wait long enough at higher values of delta t, even the higher viscosity fluid will achieve the same amount of deformation as lower viscosity fluid. So, in simple terms, a solid cares how much you deform, the stress is proportional to the deformation, the amount of deformation, while a liquid cares how fast you deform. So, a fluid resists deformation, not in the sense a fluid resists deformation by the rate at which it is deforming, not by the deformation itself. If you take a solid like steel, which is very rigid, and if you take a soft material like rubber, okay, then if you apply the same amount of stress, both of these materials will deform, but the extent of deformation will be more in rubber compared to the solid compared to the steel. Okay. Whereas here in a fluid, if you take two different fluids, one with very high viscosity and the other with low viscosity, if you apply the same amount of stress, okay, the amount at which the rate at which the fluid deforms will be different, okay, which is given by, suppose you keep the time interval constant, then that is given by the angle delta alpha. So, this delta alpha will be small for a higher viscosity fluid, while it will be larger for a lower viscosity fluid, but this delta alpha will continue to increase in both the cases. So, it is a matter of how fast the fluid deforms, and a higher viscosity implies that the fluid is going to resist deformation high more compared to the case where when the fluid has lower viscosity, where it deforms very quickly. So, it is the rate of deformation that is a crucial factor in a fluid, and the stress is directly proportional to rate of deformation. Now, this is tau ix is mu du dy, where the stress is equal to the viscosity times rate of deformation, is sometimes called Newton's law of viscosity. But you should understand that this is merely an observed material behavior, okay, observed behavior of a class of fluids. So, a Newtonian fluid is merely, or the Newton's law of viscosity, okay, let me write this as the Newton's law of viscosity, which is merely a behavior of a class of fluids, materials. Okay. It is not a fundamental law, and there are, of course, there are fluids which need not obey Newton's law of viscosity. Okay. So, but it turns out that many simple fluids like air, water, honey, and then glycerin and several oils, they all obey this behavior. Okay. So, it is a pattern of behavior that is followed by a wide class of fluids, but there are lots of exceptions to this behavior, but this is one of the simplest possible relations between the stress and the rate of deformation in a fluid. So, and fluids which obey this behavior, they are called Newtonian fluids. Okay, they are called Newtonian fluids. Now, let us work out the dimensions of viscosity, because we are encountering this for the first time in this course. So, tau ix is mu du dy, tau ix is stress, and stress is force per unit area. So, this has dimensions. We already saw this just few minutes back in the context of modulus of elasticity, and velocity gradient is basically L t to the minus 1 divided by L. So, this is simply t to the minus 1. It has dimensions of 1 over time. So, if you work this out, the dimensions of mu is m L to the minus 1 T to the minus 1. Just compare these two. In order for this equation to be dimensionally consistent, okay, then mu has to have this dimensions. Okay, viscosity has to have these dimensions. In SI units, mass is measured in kilogram, length in meter, and time in second. So the units for viscosity is kg per meter second. So this is also equal to 1 Pascal second. Okay. Now just to give you some example of various values, viscosity values that one sees in common fluids. Suppose you have air. Okay. All the viscosity values are in Pascal seconds. The viscosity value of air is about 10 to the minus 5 in Pascal second units. Okay. Water is about 10 to the minus 3, and castor oil is 100 times more viscous than water, 0.1, and blood which is a bodily fluid has viscosity of 8 times 10 to the minus 3, 8 times the viscosity of water. Okay. But interestingly, if you consider mercury, which is a liquid metal, the viscosity is very close to that of water. It is only 1.55 times larger than water. So mercury has very large density, we know that, but the viscosity is a completely different property. It is not correlated with density in any direct way, as you can see here. Even though mercury is very, very dense, the viscosity of mercury is not very different from that of the viscosity of water. Okay. So in this course, which is about fluid mechanics applied to chemical process industries, okay, we will largely restrict ourselves to Newtonian fluids, mostly. Okay. But at the end of the course, so when we say Newtonian fluids, we mean that the stress is proportional to or is equal to viscosity times the rate of deformation, which is the velocity gradient, okay, mostly. But at a later point of time, at the end of the course, we will have opportunities to talk about fluids which do not obey this behavior. They are called non-Newtonian fluids. Okay. So we will have opportunity to discuss the behavior of fluids that do not follow the Newton's law of viscosity, but for the initial part we will certainly restrict ourselves to Newtonian fluids. Okay. Now what this is saying is, if tau y x is mu du dy, if you are to do this experiment in a lab and plot the data that you get for tau y x versus du dy, okay, this is variously called as rate of deformation, because that is what it is. It is the rate at which the fluid deforms. But since the rate of deformation we showed is equal to the velocity gradient, it is also called velocity gradient. And since the deformation, the way in which the fluid is deforming is by shear, that is, you are applying a tangential force, this is also called shear rate or rate of shear or shear rate. Okay. So you should be, sometimes it is also called the strain rate, because delta alpha is a measure of strain and this is delta alpha divided by delta t. So these are all various descriptors that were used to signify the same quantity, which is mathematically du dy, which is a velocity gradient. Okay. So if you plot the shear stress versus shear rate, okay, so this is the shear rate or the rate of deformation for a Newtonian fluid, you will get a straight line that passes through the origin, okay, and the slope of this line will be the viscosity mu. Okay. This is not to say that all fluids will have the same behavior. I have told you that there are many fluids which do not follow this behavior. Let me tell you the experimental behavior that is commonly seen. Suppose you take, so these are, I am going to, the blue line is Newtonian. So let me write this in blue. Okay. So let's suppose you take solution of water and a polymer like polyethylene oxide. Okay. You dissolve very small quantities, less than 1 weight% of polymer in water, a polymer such as polyethylene oxide. So, polymer solution. Okay. And if you plot tau y-axis, if you do this experiment in a lab, you will find that it is not linear. It is going to behave like this if you take a polymer solution. Okay. This is a polymer solution. Okay. Now, if you, for a Newtonian fluid, if you have to plot the viscosity, so let me just go a little below. If you plot the viscosity as a function of shear rate, it is a constant, because tau is directly proportional to du dy and it is a straight line. So, the slope is a constant, but if you take a polymer solution, the viscosity will decrease with shear rate. So, such fluids are called shear thinning because the viscosity decreases with shear rate. But there are also fluids that shear thicken. These are colloidal dispersions. By shear thickening, we mean that the viscosity increases with shear rate. So, you could also have this behavior. Both are non-Newtonian, that is, the viscosity is not a constant, that is, or tau is not linear in du dy, but there are different classes of non-Newtonian behavior, and there is one more type of non-Newtonian behavior which I will draw in a separate graph. So, you can have a material like tar, where if you plot tau yx versus shear rate, the material does not flow up to a critical value of shear rate and it flows after that like a Newtonian fluid. Such materials are called Bingham plastics. Example is tar. Okay. So, it appears like a solid up to a critical shear stress, after that it starts flowing like a fluid. So, such materials are called Bingham plastics. Okay. So, this discussion is to just tell you what a fluid is, what is a fluid, why is it, how does it differ from a solid in terms of its deformation nature, and we saw that a fluid fundamentally differs from a solid in the way it responds to shearing stresses. A fluid, we say, cannot resist any shear stress, unlike a solid, because if you apply a shear stress to a solid, okay, it undergoes a deformation and it stops the deformation after some time. Okay. It does not continue to deform, unlike a fluid which keeps on deforming as long as the force is applied, as long as the shear stress is applied. Okay. So, a solid cares how much you deform, while a liquid cares about how fast you deform. So, if a viscous, if the constant of proportionality between the stress and rate of deformation is called viscosity, and fluids with different viscosities offer varying resistance to rate at which they deform, just as solids with different moduli offer varying amounts of resistance to how much they deform. For example, if you apply a stress of 100 pascals to a steel bar, it will deform very little, in contrast to let us say a piece of soft rubber. So, there these two materials, steel and rubber, are characterized by different elastic moduli, and a material with lower elastic moduli deforms much more compared to a material with larger elastic moduli, whereas in a fluid with higher viscosity, okay, deforms at a much smaller rate than a fluid with a much lower viscosity for the same stress that you apply, because in a fluid you can get the same amount of deformation regardless of regardless of the stress you apply, because you can always wait long enough. Okay. Now, the next topic that we are going to worry about is fluid statics. Okay. Now, so this is the first in a series of topics that we are going to cover in fluid mechanics. So far, we have been introducing the subject and introducing the notions of continuum hypothesis, what a fluid is, and so on. The first topic is that we are going to discuss is fluid statics, and what are the forces that are, how force distribution happens when a fluid is completely static, static means there is no flow, there is no motion. Okay. Okay. So, this is the topic that we are going to first discuss, and we will start from the next lecture. So, we will see you in the next lecture to discuss this new topic on the force distributions in static fluids. Goodbye.